velocity and composition of transformations. So any questions, any I don't know, comments on composition of transformations? Okay. No questions so far. So I think I will give you an additional problem straight away, problem related to the previous topic. And then we proceed with a different topic, which would be related just to several of the past problems. So, like, let me just recall the problem. Just one sec. So the problem would be following. An arbitrary triangle is considered. Like, I hope you can see my demonstration with my notebook. So we have an arbitrary triangle, like no limitations at all stated on it. So it may be like any angles, like acute angled triangle or whatever. So on the sides A, B, C of it, we consider triangles, like additional triangles. ABM, BCN, and CAP, so that angles CAP, so here we have that this angle equals to this angle equals to 45 degrees. CAP. No, sorry. These. I will first do the drawing. So actually, you can see now an example of why it's so crucial for being, I would say, not limited in solving a geometrical problem, to give yourself an opportunity to have a draft picture and I would say the main picture or the right picture, because I had some impression on the task, on the problem, and also I remember, like, I was solving the problem for maybe 10 times like during the last 15 years. But still, I can have some slightly different image of what I'm going to write, to draw, and at what particular moment it would be necessary. And depending on that, my initial triangle, like my initial picture, might become a bit false, right? And just after double checking, you'll have a sort of guarantee that everything is fine now. So we have several conditions that angle CAP equals to angle CBN equals to 45 degrees. Then angle ACP equals angle BCN equals 30 degrees. And angle ABM equals angle BAM equals 15 degrees. Prove that angle PMN equals to 90 degrees and PM equals MN. So this problem is about composition of transformations. And this is a problem from some ancient IMO, like more than 30 years ago. But still a good one, like still quite good. Because you can notice, like if you go through the problems of IMOs, that problems from the first IMOs, they would be quite different from what we have now. Many of them would be not that new now. They would be considered as some classic problems. So like the topics change. The topics change like following the degree of I don't know, research in the Olympiad topics, in the like big science topics. Okay, so this you can just screenshot, and if you get bored, you can switch to this problem if you think that the previous topic is quite understood. And by the way, like, are there those who proved the statements about composition, so that the composition of rotational homotheties would be this identity transformation, like under that circumstances, when the coefficients multiply to 1, sum of angles of rotations would be something, and so on. So any solutions of that? Because this, I don't think I saw the solution by now.
I wasn't able to fully prove it.
Okay. So do you guys want to hear the solution now?
Yeah, sure. As you like.
Okay. Yeah, okay. We'll do following. So I will tell you a solution, but it will be still okay if you send me your solutions as well. Of course, like if I count for some solutions in the end as like the final result or something, they would be counted sort of separately. Normally, they just account like the problems which were solved in class first, and then sent as your personal solutions. They are normally accounted as like fraction of the initial problem, but still it's also counted. But what is more interesting is that the solution is quite technical, though not very algebraic. And from this point of view, reproving such problems allows you to go step by step through those stages of the technical solution, like which is discussed. So I highly recommend you to not to just let it be solved in class, but also try to reformulate it and send it. Sec. So the statement was so the theorem is following. So what is the sense of the theorem? So we have three rotational homotheties with some parameters. The parameters are mentioned here. And we need to prove that under some circumstances, namely the mentioned ones, we sort of know what would be the composition. So basically, the parts of the solution we already mentioned last time. So suppose we have the three centers. So we have homotheties with center 1 coefficient. So we just denote them in the uniform way. So the homotheties will have centers C sub I, coefficients K sub I, and angles phi sub I. So phi and K were introduced in the task, and we just here say that CI, the center of the corresponding homothety. So like rotational homotheties are also referred to as homotheties. And just for simplicity's sake, we denote this as just H sub I. So then we have something like C1, C2, C3 over there. And we have these conditions. So we have that the product is equal to 1, and the sum of angles is several times double pi. So from this, we can say following. From this, we can say following. We can say that, first of all, we can track the change of length of some particular segment. Consider an arbitrary segment AB. We also have that H would be a homothety, like the composition itself, like the bigger, like the entire composition. So we will adjust the notations of the problem so that it looks exactly like this. So we first apply the first homothety, then apply the second, then apply the third, and that is exactly the entire homothety, so that we can easily deal with the notations, right? So we say that let A prime be equal to H1 of A, B prime be equal to H1 of B, then A prime, B prime they would be sent by H2 to A double prime and B double prime. And these two, they would be sent to A triple prime and B triple prime under H3. So that technically means that A and B would be sent to A triple prime, B triple prime by the homothety H, like by the composition, sorry, or by the composition H. How does it look like? Like, you should percept that if it's not very familiar, like it caused many questions to me when I was first time looking at these questions. So for me, that like the model would be following. You have a table, a firm table, which would be your model of the plane. Not very artistic. So that. So the table would be our plane. Then on the plane, like on the table, we have some paper, which is partly transparent. So we know that in principle, there are some ages for that paper. And that is one of the reasons why we know that it's not just the same as the plane itself here, right? The surface of the paper is like piece of other material. And also you have several rules how you move this paper. So you say that, okay, guys, there would be a point C1 with respect to which you take the paper and you like you take everything which was drawn on the initial plane. So you have some sort of triangle, for example. And on top of that triangle, you have like just mimicking shape. So it would be just the same shape as on the plane, but on the paper. And then you take the paper, maybe it's not the paper, but some other stretchy sort of material, and you sort of rotate this, you probably stretch it or do whatever you need, depending on the type of transformation. So it becomes something different according to the type of transformation which was taken. So most likely you had some rotations and also some other like transformations. And if you want to apply then another, so it's probably better to draw it in already rotated position. So we have something like this. So the ends of the shape or the ends of the material, which may exist, right? So probably we can apply that not to the entire plane, or some other effects may be on the edges, but normally they are just not very interesting to us, and they are quite far away from what we consider. So here, like we will have some other sort of sorry. So we have here the rotated shape. And then if we consider the next transformation, which would be performed to already this new position, the purple position of the list, it would be normally considered with respect to the point still on the table. So when that is one of the questions which was arising when I was studying these things. So we do rotate that, and we consider the new point. And what does that new point mean? Is it the new position, the old position? Like, how do we make difference between the positions? So that is what normally is supposed. So we take C2, we find where on like to which position. We even don't find, we sort of like put a nail over here, and that would be like if we speak of rotations or something related to rotation, like rotational homothety. Like we mm, like we clip the material here at this point. We unclip it here, and we perform the transformation of this example of plane with everything which was taken to this list and to this position. And we do the new transformation. So that is how it acts. So now we may be already rotating like this. So that would be the main image, how we do apply those several consecutive transformations. So normally they are defined, I would say, on the table or with respect to the table. But we apply it to the current position of the objects which we consider, which we, I would imagine that as which we took to the list of that material, which we draw there. So here, when we speak of A prime, B prime, that would be the positions of A and B on the list after the first transformation. A prime, B prime, after we unclipped the list from the first center of rotation and stretching, and clip it at a different point and apply homothety with respect to this point. And 3 primes would be one additional level of such transformation. And we eventually get something which we call H. So we just naturally deduce that A and B, they are sent to this A3 prime, B3 prime by this process. But then what we can say? We can say then that A prime, B prime would be equal to, like, the length of it. It would be equal to K1 times AB. Similar story about double primes. So under each homothety, we know that the rotational homothety, that is something we proved before during the class. Each rotational homothety is a similarity transformation, which means that it changes the length of any segment by the uniform rule. The length is multiplied by the coefficient, by the actually absolute value of the coefficient of the homothety. Because the coefficient, it may be negative. There is no issue with that. So we can say that A triple prime, B triple prime equals to absolute value of K1, K2, K3 times AB, which under the conditions of the problem is just 1. Like not this one, but the product of the coefficients is 1 times AB, so it's AB. So H is sorry, one sec. So H is a movement. It's a movement of a plane in the sense that it is transformation which preserves the length of segments. So this is sort of core property in this situation. So that means that despite the fact that we stretched the material on which we draw, nevertheless, the initial scales would be preserved, and basically that means that the entire thing could be considered as a movement of a solid body. So it works more or less like movement of solid body. That is one of the main informal properties of movements. So if we had a triangle, for example, it would be always a congruent triangle, one particular outcome. But what we need to show is rather more complicated, or rather more strong condition. We should show that it's identity transformation or a parallel translation. So that means that no, I don't know, flipping sides, flipping the material as it may happen in mirror reflection, or like no rotations should be involved when we explain what was the resulting movement. So how do we track that? But actually we track that by the auxiliary statement, which was also mentioned last time. So we can say that the direction of a vector u, like any vector of any vector u on plane, is rotated by angle phi for any homothency with angle phi. Lemma from the previous class. So what we can say then? We can say then that for any vector, say AB again, we can say that it would be rotated or transformed to some other position, maybe in some other place of the plane, right? But the direction would be rotated direction is rotated by phi1 plus phi2 plus phi3. Just one sec. By the way, like, did you hear me now when I was like referencing, like when I was sort of talking to my dog? Because like sometimes my micro isn't muted when I like muted by the means of the laptop.
So I didn't hear anything.
Okay, that's very good because I was literally shouting in microphone. Okay then. So mm, so the direction, any direction of any vector, like the direction of any vector, it was rotated literally by this angle, which is just several times n times the full angle, the entire angle, which is equivalent to 0, right? So what we know now? We know now that any vector, like for any segment AB, its length was preserved, its direction was preserved. That basically that is already actually what we want to show. So basically, what remains is to show that this is parallel translation, probably by zero vector, and that is exactly equivalent of the statement which we do. So H is parallel translation. Why it is parallel translation? Like for showing that it is parallel translation, we need to again consider a trajectory of some 2 points. Like we may say that we should consider the trajectory of one single point and show that the shift of the point is always by the same vector u, but we don't know this vector u, this vector of shift. So that means that we need to get it from somewhere, presumably from another shift of a different point. And then we just compare the shifts. So we basically can do that. So I will now finish this and then I answer the question in the chat. So following this strategy, we can again say that, okay, let's consider the points A and B. Sorry, one sec. So we consider these points A and B. This segment, we consider the segment A triple prime, B tripled prime. And we may always assume that, okay, suppose A triple prime is exactly the vector u, which we try to figure out. So we want to show, okay. So we want to show that it would be just the same vector as B B double or B triple prime. But that is obvious. Why it is obvious? It is obvious as for any A and B, B triple prime would be just the same vector as A triple prime as this figure B triple prime. A triple prime is parallelogram, like it's sort of generalized parallelogram. Is but I just don't want to spend some more time for the details here. So the thing is that we have these two segments being parallel and having equal length, right? So if they belong to two different straight lines, if they are not on the same straight line, it's quite obvious that this is a real parallelogram. It would be a convex figure, convex quadrilateral, which would be parallelogram by the inverse property. And if these 4 points belong to the same straight line, then it's also sort of obvious because like that is then just about counting the segments, like the length of a segment, like the lengths of two segments on the same straight line, right? So then we just show that B triple prime equals to the segment A triple prime, and that would be quite obvious on a straight like situation in a straight line. So that is how we prove that actually H is parallel translation. And then if like everything would be defined by an image of just one point. So if we have at least one point to which we know the result of like the resulting position under H, then we can tell which type of parallel translation is that. So if we have one point which coincides with its image, then it would be identity transformation. If we know some point for which the pre-image and the image are two different points, then it would be so for any other point as well. So the statement is that somehow this problem would be related to this theorem. Let me denote the angles. So CAP and CBN, ACP and BCN. So this would be for 13. And this would be 15, ABM, BAM. So of course, after this, it would be a good idea to redraw the picture, doing it more, I don't know, realistic. But in here, it would be not so crucial. The hint here would be that we may consider some transformations with these centers. Like, so try finding a composition of transformations with these centers, which will give you an identity transformation. Like, it would be doable, and then try to get use of it for understanding trajectories of different points. Like, for understanding that it is, for understanding that it is identity transformation, you will need to consider at least one point initially from the very beginning. But that is how you will prove the properties of the composition. In order to get use of that composition of the theorem, you need to consider some other trajectory, some other point, and intermediate positions. Okay, let's have a small break, and then we shift to a topic of masses on plane and geometry of weights on a plane. So now we have 5 minutes break. Okay. So let's continue. Like, first of all, you had this problem in your home task regarding flies crawling along some triangle. And their gravity center was mentioned. So in a sec, I'll find the text. So the text was following. And here, like, I probably will not focus on the problem now. I will just focus on the gravity center, which was mentioned here. So first of all, what is the gravity center of a triangle? Gravity center of a triangle, not... Sorry, one sec. So normally when we say a gravity center of a triangle, the reference object is gravity center of the vertices of 3 vertices of the triangle, which is also sort of a slang, because actually what is considered here would be not just the 3 points, but also it would be presupposed the points would have some weight inside of it. So for understanding this task, we may imagine just pointed weights or even just small balls of the same mass, which are placed to these vertices. And then we consider their gravity center. It's also a good question. What is that? Because we still haven't have the definition. Like, should we apply physical definition or what? And turns out that the physical definition would be to the high degree in line with mathematical definition. So in mathematics, it's not standard now, at least nowadays, to consider physical definitions of something or biological definitions of something. Like the definitions must be intrinsic to mathematics, though they would be sort of mimicking some properties, some real world properties of objects, if we want to model some objects, but they must be mathematical. So all the necessary details, mathematically necessary details, they must be included into the definition. So from this point of view, in order to mathematically discuss geometry of mass or computations with masses or whatever, we must introduce mathematical knowledge of mass or mass geometry or geometry of mass. So if we speak on plain language without special definitions of masses, then by gravity center of a triangle, we may immediately consider just the point of intersections of medians. But the real situation is, as I told before, rather more complicated. So we have at least two hidden layers of these supposed things or presupposed things, which are not quite clear. Why did we suppose it? Sorry, guys, I need just to get to my office and to a different room, and then we continue so that we don't interfere with what's happening here. One, two, three. I'm back. Can you hear me?
Yeah, we can.
Okay. Sorry. So we continue. So yeah, the gravity center of triangle, it actually sometimes would be denoted with letter M, meaning that it is intersection of medians, but sometimes it would be also denoted with point G, like being standing for gravity. And when we say that gravity center of triangle, that may mean also something different. What if the mass would be distributed uniformly across the flat surface? And that potentially may give us a different point. but it turns out, if I'm not mistaken, this question I actually like for some reasons it is met not that frequently, probably because geometry of mass is studied just for discrete sets of points in geometry and in combinatorial geometry normally. But for continuous mass distribution, that would be mostly physical topic. So, as I recall, I believe that gravity center of the triangle with this distribution of mass across the surface would be still, like, if it's uniform, that means that sort of density of mass would be same everywhere. Then I believe it's still gravity, like it's still the same point. But already I'm not so confident with that. And you may also study what will change if you consider mass uniformly distributed across the sides. So that is another understanding of the question. So what if we have, like, we sort of have zero-dimensional situation in the classical statement, like what is the gravity center? We have natural similar question for two-dimensional statement, like when the mass is distributed throughout the surface. And what if we have mass distributed through one-dimensional circuit, which would be just the sides, right? And there, I believe that the answer would be already different. So it would be not the regular gravity center of the triangle. So for discussing all these things, we probably better have finally the definitions, right? So what is system of weighted points or system of masses on a plane? So for these purposes, we actually might be interested in introducing masses of real real magnitude or real value, which may be positive but may be negative as well. So suppose we have a plane and we have points A1, A2, A3, and so on, AN. Normally the finite amount, but in principle, infinite amount would be also possible, but just when we change summations by integrals. So with these points, we will consider masses, like the values M1, M2, M3, and so on, M sub n are introduced. I would be just real number. And how we understand this, like real value for mass, like when the real value is positive real, it's quite understandable. We just imagine we put a ball of respectively small size here and of the corresponding mass. So it may be sort of heavy, but still small. And that is how we imagine point with mass. What we do if we have negative masses, like how can we imagine that? Actually, people found out how to imagine that. We may imagine this as a plane which finds some sort of support, probably. So this is something we don't consider for now. So we just have this plane. We have sort of gravity field, which means that we have the direction to which a point, like a point with mass, will be sort of applying force if the mass is put to that point. So where the force would be applied. So we then imagine that the mass is placed not directly to the point, but it is tied by a rope, by a string probably, to the point. So it's hanging down, and the mass itself is here. So this is M3. This is Mn. But also this allows us to introduce negative weights as something which pulls the plane by this point in the opposite direction. So this would be a K with mass Mk. So this would be a balloon with some light gas, which applies the corresponding force here, which would be comparable to the force directed in the opposite direction of the corresponding size. So of course that is done here not because of gravity or anti-gravity. So that is why we must adjust the mass, or the amount of the gas manually to find the proportion, so that the force would be comparable to the force which would be applying this mass if it was hand down. But then, if we skip these technical moments, we then just have that there are several masses which act downside, and there are several forces which are applied to some particular points and act upside. And that would be the model of masses on the plane. And then what is the gravity center G? The gravity center G then would be the following thing. It would be a point which may be defined in two particular ways. So definition one. The gravity center, we still haven't shown, and so we don't know that G is the unique point. So that is why we're gonna say so far that the gravity center of the system, because maybe there are many of them. The gravity center of a system of weighted points is defined like. So definition one, it's like G is such point that the sum G A sub I times MI equals to 0 vector. Definition 2 is that G is such point that for any point X, we have that sum of vectors X AI times MI, like, of course, this is summation, like the reasonable summation here from 1 to n to the total amount I equals 1 to n equals to xg times sum of the masses. So that is like this definition actually tells exactly what we expect from the gravity center, from physical statements, from any common sense statements, that for like different purposes, here I would say for many computational purposes, we can substitute dealing with the like accounting of the masses in those points. We can change, sorry, just 1 second. So we can change dealing with the bunch of these different vectors and the corresponding masses to dealing to such vector, like vector to the gravity center, and the total mass. So for some situations, that will mean that we may just change the entire system with the mass concentrated in the center. Sorry, just 1 second. Yeah. So there would be several like this is some theory, right? This is some technique, some theory. Maybe some theorems, maybe like additional theorems may be proved here. But what is the use of this? What is why it is useful? And the thing is that the use of this would be in redistribution of masses in such process, which is famous as redistribution of masses. How it works. First, the principle. Actually, it would be stated as a theorem. It would be part of your home task. So suppose we have a set of weighted points, and the set would be consisting of two groups. So this group would be group A, this group would be group B. Actually, the subdivision into groups may be even in more groups as well. So the statement here informally would be following that finding the gravity center of the entire set is equivalent to finding the gravity centers of A and B. I will denote it in the following manner. Maybe even I will adjust the picture. So if we speak of the general principle, not of the theorem itself, it would be more reasonable to say that we have subdivision into several groups. So it is literally possible that we have more than two groups. So this would be A, B, C, and altogether that would be set S. Gravity of the entire set S is equivalent to finding the gravity center of gravity centers GA with mass of A, like with the total of the masses here, then GB and the masses in the set B, total mass there, and so on. So with the subset C and so on. Why it would be important, interesting, it would be so because we may then apply. Actually, this is about something which we may understand as existence. So you know that in mathematics, like I already mentioned that, and you know that from some particular problems, for example, that if there is no object in mathematics, then we may have sort of opposite, contradicting properties of that not existing object. So if we speak of second prime even number, which doesn't exist apparently because there is just one, the prime number 2. But if we speak of the second prime number, second even prime number, it may easily have the property that it is also odd, or I don't know, like what else may happen. That it is also a third number, and so on. So that is just because it doesn't exist. So the same situation may happen with some incoherent definition. So if we have several conditions which are sort of contradicting to each other, which don't allow us to, like, not us, but which don't allow the object to exist, then we may still have those properties, but we cannot refer to the proper, like we cannot rely on them, on the properties. But here, by proving this redistribution of masses, we actually show that for most of situations in mathematical context, we may consider this as an existing and uniform object, because normally, following the physical sense, the physical intuition, we'll be considering different strategies how to compute the center of gravity, the center of mass of the system. We'll be counting it in one order, in another order. So technically, that would be accounting for it in this strategy. So we'll be finding the easiest and most reasonable way to how to find the point. But it will turn out that there is no difference in which order to do that, and that helps a lot. How we can apply this? One of the classical examples would be following. So first, an exercise example. Which also shows one of the most popular ways how to use this technique in relation to the topic of Cheva's theorem. So how to use this technique to prove Cheva's theorem? Just classical one with the segments. So Cheva's theorem statement is what? Is that if we have points A1, B1, and C1, A1 intersects B1 intersects C1 equals to point, is equivalent to A C1 over C1B times BA1 over A1C times CB1 over B1A equals to 1. Like, everyone knows and remembers Cheva's theorem. Is that right? If you don't remember that, please, like if you didn't remember that before I mentioned, please let me know with a message. Like, I definitely need to know that, because probably there is a class of related problems which I should direct you to them. So if recalling the classical Cheva's theorem, we have this. What is the relation to masses? The relation to masses would be following. So suppose let's give a proper proof of this with usage of masses. First, let's prove then part. So we have that AA1 intersects BB1 and intersects CC1 in a point. Then we do following. We then introduce masses related to this situation. So we have that this and we then call this point, I don't know, X, for example, and we then show that exists positive masses MA, MB, MC, so that X is gravity center of this weighted system of masses. So from this point of view, physically, that is almost trivial observation, though maybe not the most popular one, that for any particular point on the surface of triangle, we may adjust the weights in the vertices so that X would be the equilibrium point. So you can imagine you put this point to some support which is pointed. So imagine like those people, you probably saw those videos on internet, those who do sort of equilibrium not statues, but like compositions of stones. So they put stones one on top of another, and they put them very, very, very balanced. So they create either towers or bridges, like of course, like small ones, so that the stones they continue standing in some unrealistic position. So imagine now that a plane triangle, which is virtually weightless, like very, very light, it is put on some pointed support like this. So there is a stone, and this flat is put here. And the idea is that we can put masses solely to the vertices so that the masses would equalize the position so that the triangle will not move anymore. So that means that we can stabilize the triangle on line on that point or being supported at that point. We can stabilize it just by adjusting the weights in the vertices. How do we do this? Actually, quite easily. We should study how to do that just to one vertex. Just along one segment. So what I want to do, I want to be sure or to get sure that if I have a segment AB, then for any position of point C1, I can get this as a gravity center of these 2 points, and that would be actually both necessary thing. So if we cannot adjust the masses along a segment, then hard to expect that from larger amount of points. But also as in induction, we will have this just the first step, which will actually generate all the next steps. Because if we can adjust that in a group of 2, then you can imagine some situation like this with redistribution, that we take then the group of 2 points and 1 point in another group. And that is how we can use some principle for system of 2 points applied already to 3 points, right? So we apply to 1 point and to this gravity center of other 2 points. And we have something about 3 points, but then we can again increase the amount by 1 because we'll be referencing again gravity center of a group of 3 points, for example, and another point. So coming back to this, we have some particular length of this segment, which is even not that interesting. We have some particular ratio here. So that would be alpha and 1 minus alpha. So alpha then equals to AC. Let alpha equal to AC1 to AB. Then what masses needed to be placed to these vertices so that the equilibrium holds? Like it's also not that clear what is equilibrium here and why I refer to physical intuition, because the relation still is not clear. But that is something which we may keep in mind, that would be related, and we the only complicated part would be rather giving mathematical proof of a statement, even if the statement came to our mind just because of some physical intuition. So here I how it's called, like I came to this idea of equilibrium by considering the classical situation for centers to center of mass in physics. when we consider swings, or when we consider a lever, so there is some support for the lever, and there would be length 1, length 2. Here would be mass 1, mass 2. They would be applying force to the endpoints here. And we know that the lever or the stick, it would be stabilized just if the momentum of force would be equalized. So that is how we know that M1 L1 equals to M2 L2. This would be physical intervention. So here I would try the same. I would try applying here mass MA. I would take MA equal to 1 minus alpha, and MB I would take alpha. And then I check by definition, right? So by this definition, the point which is gravity center should satisfy this equation. So we will have some technical statements in the home task, which would be theorems. First of all, that these two definitions would be equivalent, probably with some limitations, like that the mass, like for masses greater than 0, or for masses so that the total of masses is not equal to 0. Then the gravity center would be unique point, and these two definitions would be equivalent. But as for now, we just use that it is unique, and that we may choose any of these two definitions. So I will use this definition to check. So we check C1 as gravity center. C1A times MA plus C1B times MB. Is it equal to 0 or not? But we can easily see that it is equal indeed, because we have what? We have that passing to just segments or segment lengths in one particular direction. We have that here we have C1A times MA minus C1B times MB equals to 0. And C1A is alpha L, MA is 1 minus alpha. So we have alpha L times, 1 alpha times AB times 1 minus minus 1 minus alpha AB times alpha. It is 0 indeed, right? So that is how we show that this intuition from physics, or this lever rule, it really applies here. It gives us the right intuition along the segment. So we may choose weights in such a way that the gravity center of those 2 points would be exactly C1. So this would be technical lemma. So then we put MA and MB so that the gravity center of these two is C1. And we then, so we choose MA, MB so that C1 is gravity center of AMA and BMB. And also we choose MC MC so that A1 is gravity center of B and C. So like in shorter way of writing that down, we just mentioned the points, right? But we remember in which order and with which definition they are chosen. But if we take such MC, yeah, then we have actually we can make two observations. Like first of all, the ratio of AC1 to C1b, which is here just alpha to 1 minus alpha, it would be actually just the reciprocal ratio of the masses in A and B, right? Alpha to 1 minus alpha would be equal to MB over MA here. So that would be basically the ratio of segments would be a crisscross ratio of the masses. But then it becomes very, very observable why, if we have the point, why we have the product equal to 1. So at least these two ratios, they would be just AC1 to C1b. It would be just MB to MA. This ratio would be just MC to MB. So technically, if all three of them would be ratios of masses, we easily can see that it would be, or the product would be 1. But what we don't have now, we don't have the ratio here equal to masses. We still sort of don't know if it is really the ratio of the masses. So the question is it true then that B1 is the gravity center of A and C? And it is indeed. We can then say that it is really the center of mass of them, but we can say that without any calculations. Why is that? Like probably with very schematic calculations. So if we choose the point, the mass MC in this manner, Then we have following. Let's consider, we consider G, the gravity center of these three weighted points, A, M, A, B, M, B, C, M, C. Then, by theorem of redistribution, which would be a theorem in your home task, but here we just which would be proper mathematical theorem, but here we mentioned this as some physical principle and something to be proved, but it is really provable, and you will do that. So by the theorem of redistribution, G is also gravity center of A and B, and MA plus MB as one point. So we change the subset of points A and B, weighted points A and B, to their gravity center with the total mass. And the second point to consider would be C and mass MC. And this point here, just by the choice, is the point C1 by choice of masses. But then, as G is the gravity center of these 2 points, that means that it belongs to the straight line on between that points. We could observe that here, though it may be also some auxiliary statement to prove, but it's more or less clear, because you can easily check that if you have if the point is not on the straight line, then the sum, at least if we have positive weights, then the sum of the weighted segments, it would be it would be not on the line, basically. This sorry, yeah, the sum of those, it's not quite correct. The sum of those vectors, it would be just opposite. It would be on the line. It wouldn't be 0. So for any other point, for a point outside of the straight line, the sum, which must be 0 by the definition of gravity center, it wouldn't be equal to 0, because it definitely would be like, if point is here, then definitely the sum would be like below it, for example. So by very similar observations, like in general case, we will have that. Okay, so we have this. So G is on C1C. So G would be belonging to this segment. But also similarly, it's on A1. Why is that? It's just because the gravity center of these two, we also know it's A1. So the gravity center of the entire system, by the redistribution, it would be on this segment as well. So it's on A1, AA1 intersected CC1. It's on the common point of these two. So G is equal to X. That is how we just showed that these two conditions on the masses, it's enough to show that G, the gravity center of the entire thing, is actually coinciding with X. But then we can also say that the gravity center of these two, it must be B1. Why is that? Just because if we have any other point, then the gravity center of the triangle of the vertices, it would be a point on this line, right? The gravity center of these two, somewhere over here, by assumption not equal to B1, and the B. But this segment, it just doesn't pass through X. That means that G, the gravity center of the entire thing, cannot coincide with X then, which is clearly a contradiction because we just showed as a property that G coincides with X. So that's how we prove that adjusting masses, these three masses, so that these 2 points are gravity centers on these two segments, it's enough to have this point, the gravity center of these two masses. And that is seemingly that is some physically geometrical property of matter. And that is why geometry would be so helpful in physics like related to masses. So that is how we now know that each fraction here over here, it would be just equal to a fraction of two masses. And like you can easily check that the masses would be going in such an order that all of them would be canceled out as the result. So we will have the thing equal to 1. In the opposite direction, it would be more or less equally difficult. So we just take two masses adjusted, like these three masses adjusted on two segments. We check that on the third segment, what we want is actually what we have. And then we say that, okay, that guarantees that the gravity center of the system is belonging to this segment, and to this segment as well. So they all intersect in the same point. That's it for now. Any questions? Okay. If no questions now, then please feel free to ask them on chat. And oh, sorry. Just one sec. Yeah, so feel free to ask them like as normally as like as all of you did, as part of you like regularly do. Like please keep in touch with me on chat. You will have the list of the proper list of the problems about this, and like probably something about the previous topics as well. And I think I will introduce this spreadsheet of the solved problems. So feel free to submit some previous problems as well. So as to me, at least, it's not a competition during the training. Like it's different purpose of things, of solving problems. So it's more about discipline. So how many problems did you solve? And what is your progress? You'll learn this. So that's it for now. See you next time, and keep in touch.